Welcome back to fatigue failure theories. We'll continue with designing for fluctuating uniaxial stress. Okay, so in these graphs, you will see repeated and fluctuating dynamic load. So for the repeated one, sigma minimum is 0, but none of the sigma m and sigma a are 0. And for the fluctuating, nothing is 0. So the point is that for both of these cases, sigma m is not 0, as we have studied for fully reversed uniaxial stresses. Now we want to see how we could develop a theory to find the safety factor under fatigue loads. So different people use experimental data and theories to find the safety region. So in this graph, you see the y-axis is sigma A or alternating stress, and x-axis is sigma m or mean value or static stress. Here, the maximum stress could be SF or the fatigue strength. And here, the maximum could be either yield strength or the ultimate tensile strength. And any of these theories are using a combination of them to define a safe region. So this is a safe region inside, and the outside, the material fails. The best one, and the one that we use, which is conservative enough and near to empirical data, are modified Goodman. So we go to the more detail of modified Goodman theories. And what is that exactly? So again, here we have the same axes. We have the vertical axis of sigma A and the horizontal axis of sigma m. On the vertical one, you see that here the maximum could be SF or fatigue strength, and on the x-axis the maximum could be either yield strength or ultimate tensile strength. And the better and the more conservative one is to take into account basically the yield strength. Connecting those points and triangles, you could have the safe region for the tensile stress, tension stress and compression stress. Okay, what is the formula of this line could be calculated by this formula. We will explain these regions in more detail. Okay, so here again you have it, and you see the equations on each line. What are there exactly? On AG, this is the yield in compression. Equation BC, a fatigue failure from plus compressive mean. Equation CF, fatigue failure plus tensile mean, and equation GE, this one, the yield in tension. Okay. The first one that we explain, and the most important one for us, is equation of CF, this one. Okay, so let's see the more detail here and different cases and scenarios that could happen. So here you see the safe region and the load line. Okay, so assume that the alternating effective stress for one particular example is sigma prime A, and the mean value of the alternating stress is sigma prime M. So we are at the point Z. The first case, or case one, is the one that the the sigma A or alternating component is constant, but the mean value could change. So if that's the case, then this will be the load line. Why? Because you see that sigma prime A is constant and sigma prime M could change. And eventually the load line will cross the safety border here at the point Q. And once that happens, the safety factor will be equal to 1 at the point Q. Well, what is the safety factor then at the point Z? Is this one, NF. NF is equal to sigma prime M at the point Q, okay? So sigma prime M at the point Q divided by sigma prime M at the point Z. And this gives us the safety factor, which is more than 1. And, or basically we could calculate this by this formula, which is equal to Sy divided by sigma prime M multiplied by 1 minus sigma prime A divided by Sy. So once we have the yield strengths, sigma prime A and sigma prime M, then we could find the safety factor. This is the case 1. Case 2. Sigma A varies and sigma M is constant. Then this will be the load line. Okay, and we will cross the borders at point P. So safety factor is equal to the sigma prime A at the point P divided by sigma prime A at the point Z, or alternatively could be calculated by this formula. Again, safety factor is more than 1 once the point Z is inside the safe region. Case 3, sigma A divided by sigma M ratio is constant. So if that's the case, then the load line will be something similar to this. And we basically cross the border at the point R. Then we could calculate the safety factor by this formula and say is equal to the sigma prime M at the point R divided by sigma prime M at the point Z, or alternatively from this formula. And finally, the case 4, which is a general case for uniaxial cases, once both sigma A and sigma M would vary independently, then we need to find the smallest safety factor, and that will be at the point S. Why? Because you see that this is the smallest distance to the border of safety. So we need to calculate these distances and say that safety factor is OZ plus ZS divided by OZ. And the ZS and OZ could be calculated by these formulas. We need to see, based on our problem, what cases we have for dynamic uniaxial cases, and choose a proper formula, safety formula, and plug in the numbers into the equations. For the stress concentration factor, since we have also the mean value, we need to find a mean value of the fatigue stress concentration factor, or KFM, which we didn't have for fully reversed loads. If the material is brittle, then KT is used to find mean stress fatigue concentration factor, KFM. Okay, so it's very simple. For brittle material, just use the same KFM is equal to KT. For ductile material, then we need to check these conditions. If Kf multiplied by the maximum nominal stress is less than Sy, then Kfn is equal to Kf. If it's more than SF, then we need to use this formula to calculate Kfm. And if it's more than 2SF, then the Kfm is 0. The local applied stresses are used to calculate alternating and mean value of von Mises stresses. Let's go through this example, very similar to the previous one, but the load type is different, it's fluctuating. So we have both mean value and the alternating value. So very similar, the feed roll, and the feed roll experiences a total fluctuating load that varies from a minimum of 200 to a maximum of 2200 pounds. Split equally between the two support brackets. We have two support brackets at the left and right. Design a cantilever bracket to support the fluctuating bending load of 100 to 1100 amplitude for 10 to the power of 9 cycle with no failure. Its dynamic deflection cannot exceed 0.02 inch. So you see that we have a mean value, max value of the alternating force. And based on that, we should proceed and do the calculation. Very similar to the previous one, but there are slight differences. So it's worth to follow the steps and do the calculation again. The operating environment is room air at the maximum temperature of 120 degrees of Fahrenheit. The space available allows a maximum cantilever length of 6 inch. Only 10 of these parts are required. So you see that KT is given, and we will proceed with this KT in our calculation. Okay, so we need to find the forces and moments. We need to find the mean value of the force and the alternating value of the force, which was not the case for the previous example of fully reversed one, because we didn't have a mean value, we only had alternating value. Then we could find the reaction, alternating reaction forces and the mean value of the reaction forces. And based on that, we could find the mean value of the bending and stress and the alternating value of the mean stress. The moment of inertia and the maximum distance from the neutral axis is same as before. Now we need to calculate the nominal bending stresses, but now we have both alternating nominal value of stresses and the mean value of the stresses. So for both of these cases, we need to plug in the alternating component and the mean component of the bending moment. Once we do so, then we have these sigma A and sigma M values. Now we should proceed to find geometrical stress concentration factor and finally the fatigue stress concentration factor for both alternating one and for the mean one. So we calculate the KT as we did before. We will end up with the same number. And Nuber's constant should be calculated. So we will repair to the tabulated tables, and we could find the Nuber's constant as before, very similar. Knot sensitivity factor is same as before. And now we could find Kf, fatigue stress concentration factor, based on the KT, which was given on the figure. This is the one for the alternating component. For the KFM, we need to check our conditions. Since the Kf multiplied by the sigma max is less than Sy, then Kfm is equal to Kf for this case, and the Kfm is also equal to 1.16. Now we have Kf and Kfm. We should multiply them by Ka and Km nominal to find sigma A and sigma M. Once we have them, then we could proceed to calculate the von Mises effective stresses for both alternating and mean value. So we have sigma prime A and sigma prime M. So you could either use these formulas for applied stresses, or you could find the principal normal stresses based on Mohr-Zirkel, or the other formula which was based on the principal normal stresses for the effective von Mises stress. Now we have sigma A and sigma M primes. Now it's time to find a fatigue strength very similar to the previous steps. We could find the uncorrected endurance limit. Then we will proceed to calculate the reduction factors for the size, for the surface, for the load, for the temperature, for reliability, and we could multiply all of them to the uncorrected endurance limit to find the corrected endurance limit. Okay, now we have all of the numbers. Now we need to see what is our case. The case is case 3. Why? Because the sigma A and sigma M are in a constant ratio. We have both of them. If F increases, both of them will increase proportionally. So we should go for the case 3 safety factor, which assumes that the alternating and mean components will have a constant ratio if they vary in maximum amplitude over the life of the part. Again, why? Because you have a force at the tip of a cantilever beam. If that force increases, both the mean value and alternating value will increase proportionally with the same ratio or constant ratio. So now that we identify what is our problem case, then we will use a proper safety factor based on the case 3. And we have all the numbers. We need to plug them into the formula. Endurance limit, ultimate tensile strengths. We have effective stresses, alternating and mean value. And now we see that the safety factor is 1.9. Magically, very nice safety factor. Okay, but of course it's not the case always, and you need to go through iteration and change the sizes and materials to find the proper safety factor. For the sake of homeworks and let's say final exam, one iteration will be enough and will be acceptable if you just mention that, for example, the safety factor is not proper, so we need to go through iteration. That's it. For the deflection, again, we use the cantilever beam and the maximum forces, and we see that also the deflection is inside acceptable range. So we are done and we are good for this specific example. Nothing else we need to